All right, so boundary conditions. Let's apply two appropriate boundary conditions to this problem. One is going to be our boundary condition T at R equals, let's say R sub I, that's what we call this, equals the steam temperature. And our other boundary condition is going to be balancing then the flux at the outer wall. We're going to put a thin boundary here and balance the convective rate equation. Q is H AS delta T with Fourier's law, with the diffusion through the material. Q is negative K AS dt dr. So this is what we need to use as another boundary condition. It looks like they both have the surface area, so if we set this equal to this, we can let that surface area cancel. And now here's where at the very, very, very beginning of the lecture I said, oh, well, a lot of times we use TS. We would write this as the surface temperature minus the fluid temperature, so TS minus T infinity. We've already used S for steam, so we're going to use T naught, T O for T outer radius. O minus T infinity, where that was the fluid temperature. So these are the two boundary conditions, but we have to be a little bit careful. This TO should be a function of the radius. We have a very large radius or very small radius. It will make a difference. So we'll have to be a little bit careful. That's TO of R.
Professor.
Yes, sir. Yeah, that was after we took the limit. So basically we took some inner radius and some outer radius separated by a delta R. We did the limit as the delta came to 0, so we really did have one area of interest. Yes. Okay, good. And please, stop me, absolutely, if we have any questions, especially today. I am feeling actually a lot better. Yeah, we will keep going with this and get through it. All right. So this one, so I was saying this is actually T of RO. Right? We can evaluate this function, T of R, at RO and plug that in here. So you see my nice map here. I feel like a soccer coach or something, but yes, that's our game plan, is to take this function, evaluate it at RO, plug that in for this second boundary condition. All right, so will it help us to evaluate at RI first? I'm not sure. If this is like 0 or something, we might be able to cancel, but we can start applying any of these. Let's start with T of R equals RI equals TS. So this equals T of R evaluated at Ri, so we're going to plug in C1 natural log of Ri plus C2 equals Ts. Excuse me. Plus C2. And that equals to Ts. So again, we can solve for either one of these. We can write C1 as a function of C2, or it'd be pretty quick and easy to write C2 as a function of C1. C2 equals Ts minus C1 natural log of Ri. The other boundary condition that we have here is negative K dt dr. So actually, I'm going to cheat a little bit, and I already know what dt dr is. It's up here. So negative K times C1 over R equals H. We need to evaluate this. T of R naught is going to be C1 natural log RO plus C2 minus T infinity. Alright, so we have negative K. And then dt dr was just C1 over R equals H. We have T of RO C1 natural log RO plus C2 minus T infinity. H delta T, that is it. So those are the two boundary conditions we need to solve. We need to solve for C1 and C2.